Hello, everyone. This is the lecture for section 5.5, substitution. So in this section, this is going to be the very first, the most basic integration technique that we're going to be covering, at least in Calc 1. This integration by substitution is going to keep going. It's going to happen even more once you get into Calc 2, okay? This is the, like I said, the most basic one, right? All the other sort of integration techniques that you're going to learn in Calc 2 are basically sort of either this exact thing, right? Or just a little spicier than just this regular U substitution, okay? So in this section, what I'm going to do is I'm going to present it for you guys, right? This is one of the sections where I tell people, like, if you need more practice, go into any calculus textbook, any one that you can find, right? Open it up to this section for U substitution, right? And just practice, 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 practice. There's going to be a couple of things that you're going to need to be able to sort of identify, right? When you look at these in order to perform integration by substitution properly, okay? So let me first go into why we have it, okay? So let's go ahead and consider this function right here, f of x, right? If we take the derivative of f of x, we get this thing, right? So hopefully you guys are, you probably already thought of this, right? That in order to take the derivative of f, I need chain rule because there's an outside and there's an inside. So the derivative is that thing right there, right? And I left it as most of you guys would without expanding it, just like that, right? So we needed the chain rule to take this derivative, right? Since the integral, right, and the derivative are sort of inverses of each other, right, then it stands to reason that if I take the integral of this derivative, things should, like the integral and the derivative should cancel out. I should get back my original function, my f of x, right? That is, if I take the integral, right, of the derivative, that's the same thing as doing this, right? Which means I should get f of x back plus a constant c. So my integral should be this, right? And that's solely by taking the integral and the derivative as sort of inverse operations of each other, okay? So if you have the integral of a derivative, right, they should cancel out. If you have the derivative of an integral, they should cancel out, okay? So what I want everybody to see is this, that the function itself, this function right here, right, we got this derivative using the chain rule. We got this derivative using the chain rule, right? And we were able to integrate, right, and get the original function back. Got it? That is the impetus for integration by substitution. What we're essentially doing, right, is we're performing an integration, right, that was produced using the chain rule. We're performing an integration on a function that was produced using the chain rule, okay? So essentially what U substitution is basically undoing a chain rule derivative, okay? That's why we need it, okay? So now let's go into the actual theorem for integration by substitution. Let U be g of x, g prime be continuous, little f be continuous over the corresponding range of g, and then let big F be the antiderivative of little f, right? Then the integral, right? Notice how the integrand, the thing that's inside, like between the dx and the squiggle, right? That looks like a chain rule thing, right? Then this integral can be substituted like this, right? It's going to be equal to f of u plus c, which is equal to f of g of x plus c. So what happens here, this is the reason why it's called U substitution. The U is equal to some g of x that we have to choose, right? More importantly, we have to choose it. So notice what happens, right? This gets substituted, right? And then this, all of this disappears into a du, okay? That, in essence, is giving us sort of like a game plan or a problem-solving strategy for how to do integration by substitution, okay? So let me cover the steps for that are right below it, okay? Number one, for step one, look at the integrand, look at the stuff between the dx and the squiggle, right? And select your expression g of x that's somewhere within the integrand, right? Set it equal to u such that its derivative is also in the integrand. Does that make sense? So you want the thing, right? You want the thing, g of x, to be something where the derivative is also inside the integral somewhere. Okay. Step two is you do the substitution, you let u equal that thing, gx, right? And then you take the derivative and substitute that into the integral as well. Okay. Step three, what happens at this point, once you do the substitution, the u substitution, and then you do the du substitution, right? What should happen is that your integral must become much, much simpler, okay? If it doesn't get much simpler, then you got to go back to step one, choose a different u, okay? Then you evaluate the integral in terms of u, so you perform the integration, right? You find the antiderivative in terms of u, right? And then step five is you undo the substitution, okay? So let me go ahead and show you guys a, oh, I should mention that this problem solving strategy is, like it says there, it's modified. There's a couple of things that, that I didn't like about it that I think is crucial to be added into the problem solving strategy if you guys are solving by the problem solving strategy, right? Like in particular, a version of G prime, okay? So not only does it have to be G prime, it can be any version of it. So I'll do an example to sort of demonstrate what I'm talking about here, okay? So now, let me do this first one, okay? So this first one, if you guys take a look, x squared plus 1, right? The derivative of x squared plus 1 is the 2x. So I have here, right, I've sort of identified the thing where the derivative is also inside the integrand, right? So that's the thing I'm going to set equal to u. So I'm going to say u is equal to x squared plus 1, right? And then I'm going to do du over dx. I'm taking the derivative of u. I'm taking the derivative of my substitution, that one right there. Okay, I'm going to take the derivative and I'm going to get 2x. I'm going to arrange this nicely so I can get du is equal to 2x dx. Okay, I'm going to rearrange this a little bit. I'm going to do the integral, right? X squared plus 1 cubed times 2x, I'm going to put this in parentheses, dx, okay? And the reason why I did this is because now I get to, I basically group stuff together, that's it. My u is that thing, right? And my du, well, yeah, my du is this thing. So what happens is this, I get to change my integral. My u was the x squared plus 1, so this is now u cubed. And du is 2x dx, that's grouped right there. So this is now du. So now I'm going to evaluate this integral in terms of u. Okay, that means I'm going to evaluate this thing just as normal. Notice that this is much more simpler than what it was originally, right? The integral here, right, is going to be u to the fourth over 4 plus c. And this is the point where I undo my substitution. So my original substitution is this, right? So I just get to undo it. So this is x squared plus 1 to the fourth over 4 plus c. And we are done. We have performed our first u substitution. Okay. So this doesn't only work with just, polynomials. It can work with other ones. Let's do the one that follows. Okay. The integral of 10x times sine 5x squared plus 3 dx. Hopefully you guys have already identified. So my u, I need something where the derivative is also in there, right? The derivative of 5x squared plus 3 is 10x. So I'm going to let u equal that. So then du over dx is going to equal 10x, which means du is dx, 10x dx, right? Is equal to the integral. I'm going to rearrange just like I did above, right? Sine of 5x squared plus 3 times 10x dx. Now I get to do my substitution here. So it's going to be the integral of sine of u du, right? Because the u got to turn that thing into u, right? And this stuff, 10x dx, got changed to that. The integral of sine of u, right? If you guys remember the circle, right? Let me do sine and then cosine, right? If you go this way, positive, and if you go this way, it's negative. The original circle, right, was for derivative. So the derivative of sine is cosine. The derivative of cosine is negative sine, right? The backwards is the integral. So the integral of sine is negative cosine. So this is going to be equal to negative cosine of u plus c. I undo my substitution now. Negative cosine of u, 5x squared. Well, let me make it look nice. 5x squared plus 3 plus c. And we are done. Okay, so these two that I just did, they're sort of the basic versions where the derivative is an explicit, like the derivative is actually in there, right? So in the first one, the derivative of x squared plus 1 is 2x. That is explicitly in there, right? In the second one, the derivative of 5x squared plus 3, that is 10x, which is explicitly in there. I didn't have to do any fumbling around with it, right? Okay. The next one I'm going to do is what I'm talking about in terms of a version of the derivative. Okay. So hopefully you guys are looking at this and you're thinking, okay, it's got to be, u's got to be this, right? And then the rest of the stuff should be, the du, right? But it's not exactly it, right? So let's go through the steps here, and I'm going to show you guys what's going to happen. So you guys are right in the thought that that's going to be u. So I'm going to set u is equal to 2x squared plus 5x, right? Then du over dx, if we take the derivative of this, right, this is going to be something 4x plus 5, okay? Which means, right, du is equal to 4x plus 5. I'm going to put this in parentheses. Whoa, parentheses. 4x plus 5 dx. but we need 8x plus 10, right? This is where we're going to do the, it's a version of the derivative, right? If you take a look at this, if we multiply both sides by 2, we get my 8x plus 10. Does that make sense? So I'm going to do that exactly. Times 2 times 2. So then I get this. 2 du. Let me write it in here a little bit more. 2 du is equal to 2 times 4x plus 5 dx. So then now we get 2 du is equal to, this is going to be 8x plus 10 dx. Now I have the derivative that I'm looking for. Does that make sense? But in this case, I had to multiply it by 2. So now my substitution is going to be 2 du. Okay, so let's go ahead and go from here, right? So this is going to be the integral, right? The sine of the 2x squared plus 5x. That's its own thing, right? And I'm going to group the other thing over here. 8x plus 10 dx, right? This is now equal to the integral sine of my u is still there, right? Now I get to perform this substitution right here. This is going to be times 2 du. Okay, so my u, right, changed that thing. And then all of this, right, because of this, became our 2 du on the other side. Okay. So this is, now I'm going to use one of the principles from integration. Since there's a constant in there, it's times 2, right? That 2 gets to pop out. So this is equivalent to 2 times the integral of sine of u du. Okay. We're going to use the same thing that we did before, right? We know that the integral of sine is negative cosine. So this is going to be 2 times negative cosine of u plus a constant c. So it's going to be negative 2 cosine of u plus c. And now I get to undo my derivative. So negative 2, negative 2 cosine of my u, which is 2x squared plus 5x plus a constant c. And we are done. Okay, and just for verification purposes, I'm not going to do it, but you guys should at least sort of observe this or recognize this, that if I grabbed this, right? If I grabbed this and I took the derivative of it, it's gonna be this. Okay. Likewise for the ones from above, from before, right? If I get this and take the derivative, it's gonna be this. And if I grab this and take the derivative, it's gonna be this. Okay. Okay. So now that we know how to do indefinite integrals, right? Let's move on to doing definite integrals with u substitution. Okay. So same idea, right? So if we let u equal the g of x, right, where the derivative shows up in the integrand somewhere, f of x, little f of x, let it be continuous over the range, not the over the Grange, huh? Over the range of u of x, and let f of x, big F of x, be an antiderivative of little f of x. Then you have this equality. And I want to explain the equality really quick, okay? The integral, the definite integral from a to b of f of x, f of g of x times g prime dx, okay? Because of the substitution is equivalent to this integral right here, right? Okay. Which is equivalent to this end right here, f of v minus f of u. This is just sort of, if you guys remember the evaluation theorem, the second fundamental theorem of calculus, that if I have the antiderivative, then I can just plug in the lower limit, the upper limit, and then subtract them, okay? Which is equivalent to this right here, okay? And this is basically undoing the the substitution from the very beginning, the u equal gx. Okay. Now, this brings up two different methods for solving the same definite integral. I'm going to show you the first one, which is I'm going to show you both, right? And I'm going to sort of explain which one I like better. I like doing the one where you undo the substitution. Some people don't like undoing the substitution. It just requires a little bit more work, but you know, it's meh, whatever, right? Okay, so let's go ahead and perform this definite integral. Okay, so we're going to start off the same way. I hope you guys see what the derivative is going to be already, or at least I hope you guys see what the u substitution is going to be. It's going to be this right here, right? So if we let u equal x cubed plus 8, right? Then du over dx is going to be 3x squared, right? And I need to modify this a little bit. So it's going to be du is equal to 3x squared dx, right? But I need x squared, right? So I just need this portion right here, just this, without the 3, right? So I'm just going to divide by 3. Divide by 3, divide by 3. So then du over 3 is equal to x squared dx. Now I have the thing that I need to group together. Okay. So now I'm going to go from here. So this is going to be equal to the integral. Okay. And I'm going to go ahead and do this really quick. I'm going to explain why I'm going to do it a little later. Okay. X equal minus 2 to x equal 4. X cubed plus 8 cubed times x squared dx. So all I did was rearrange the furniture so I can get everything to look like what I just did down here. Okay. This is now going to turn into, and I'm going to drop the integral, the limits of integration for now, and I'll explain why right now, but I wanted to put them there first, like that, before I moved on. So this now substitutes to u cubed, right, times du over 3, right? So let me go ahead and explain why there. That was my u, and this is the substitution for the x dx, sorry, the x squared dx, right? And then that substitutes down to that. So then now I get equal to, this is an over 3, so this is a 1/3. I can pop the 1/3 out. So 1/3 integral u cubed du. Now this right here is much simpler, right? Okay, let me do something here. I'm going to grab this, and I'm going to move it up here. I'm going to put an arrow toward it. I kind of want to leave as much space as possible for the two methods. So this is where the evaluation process sort of splits into the two methods, okay? And let me explain how those work, okay? I'm going to come down here, and then I'm going to draw a straight line down, okay? From the theorem, right, I can either, I would want to say it this way. These two would match. This one and this one would match, right? And the other one, this one, and this one would match. They're all equal, right? They're all equal. But the difference is in the pink ones, in the outside ones, right? We are going to undo the substitution, okay? And do it as normal as we would do before, okay? In the green one, we're basically saying we're gonna keep the substitutions, but in order to keep the substitutions, we need to change the limits of integration, okay? The original problem, the ones in pink, right? The limits of integration are for a variable x, right? Whereas the ones in the green, the variables of integration is for a substituted function u, right? And that substituted function u is based on the x values. So in order to get the u values, right? In order to get the u values, we need to substitute the x values into the u values, and then we can keep the integration. We don't have to undo anything. We don't have to undo a substitution. Okay. What does that mean? Let me go ahead and explain what happens. So technically at this point, this is where the two methods sort of separate. Okay. So at this point, right, we know what the integral of this is, right? So the integral, we're talking about here. So I'm going to keep going from this point right here. Okay. We know what this integral is. This is going to be 1/3 times u to the 4th over 4, right? Okay. This is going to be equal to u to the 4th over 12. Okay. And now I get to undo my substitution. So this is actually equal to x cubed plus 8 over 12, and this is going to be to the 4th, evaluated from -2 to +4. Okay. So notice what I did. I used the u substitution just to do the integral, right? I did the integral, and then I just undid the substitution. And since my original limits of integration were for an x variable, I get to keep the 2 and the 4. So then at this point now it's just plug and chug. So this is going to be 4 cubed plus 8 to the 4th power divided by 12 minus -2 cubed plus 8 to the 4th power all over 12. Okay, this is now equal to handy dandy calculator. 4 cubed plus 8, and that to the 4th, something massive, divided by 12. 2,2,3,9,4,8,8 minus -2 cubed plus 8 to the 4th divided by 12, and that is 0. So this is equal to 2,2,3,9,4,8,8, and we are done. We evaluated it. That's it. Okay. This is it. This is an answer. This is the answer for this problem, right? Okay. Awesome. So this one's the one that I like to use, right? Because I usually don't want to undo the, I don't want to recompute some limits of integration, just because I don't want to. That's it. Okay. So this one, we use the u substitution just to perform the integral. After that, we threw it out. We didn't care, right? Okay. The other method, right, is essentially saying we keep the substitution, right? But that means we have to change the limits of integration. Okay. So what does that mean? So x, whoa, wrong color. So let's take the very first limit of integration. X is equal to -2, right? We know that u is equal to x cubed plus 8. So then we perform that substitution, right? So then that means u is going to be equal to, substitute, -2 cubed plus 8. We know that this is 0, right? And then if I do x is equal to 4, so that means u is equal to 4 cubed plus 8. Oh, and I forgot to cube this. Aha. Oh, no, never mind. Take it back. That's the u is just x cubed. Haha. Look at me go. That's going to be, let me compute that. I think it was like 72 or something. Come on, 4 cubed plus 8. Yep, 72. Okay. So that means that what we did, right, is this. I'm going to rewrite it from sort of like the very beginning. The integral, right, from x equal -2 to x equal 4 of x squared x cubed plus 8 cubed dx is equivalent, using the same substitutions and using the same du's and everything else, right, is now equal to the integral from u equals 0 to u equals 72. And I forgot the 1/3 here, of u cubed du. So notice what happened, right? I did the substitutions for all of this stuff. That turned into this, right? And my limits of integration changed. Okay. I get to perform the integral as normal. So this is going to be equal to 1/3 u to the 4th over 4, right? Which is equal to u to the 4th over 12, evaluated over the new limits of integration, those two. So this one is going to be from 0 to 72. Okay. Now I don't, at this point, I did the substitution. I don't have to undo it because I changed my limits of integration from the x variable into the u variable. So now all I get to do is this. This is equivalent to 72 to the 4th over 12 minus 0 to the 4th over 12. Those are the new limits of integration. And if you do this, you get 2, 2, 3, 9, 4, 8, 8. Same answer as the other side. And we are done. So at this point, depending on how you want to solve a definite integral, right? It's up to you, your flavor. I highly prefer this one, right? I highly prefer this one because I don't like doing this bit right here. Okay. Sometimes it's useful. Sometimes it's useful to do the to not undo the substitution. Sometimes it is. Most of the time, I think it is useful to undo the substitution. So that's, so at this point, it becomes your personal preference, whichever one you want to do. Either way, if you do it properly, you get the same answer. Okay. I am done, I think, because after this is lecture questions. So notice that this one doesn't have quick checks. Thank goodness. Take your time to learn this section real good. Um, practice for your practice for the final, and I'm gonna have the final open till the very end of tomorrow. Okay, so make sure you study up. I'll be in my office hours in my Zoom room from 3 to 6 today, and I'll be around on my phone um, all day tomorrow. Okay, at least be really close to a something with internet. So if you guys have questions, email me ASAP. Okay. Besides that, I'll see you guys around and hope you guys are studying real hard.